Drop an ice cube into a glass of water. It floats. You have watched this happen 10,000 times. It is as ordinary as anything gets. Now try to name one other solid that floats in its own liquid. Iron does not float in molten iron. Wax does not float in melted wax. Rock does not float in lava. Almost nothing does this. Water is the exception. Ice floats. It is the only reason anything in the ocean survived the ice ages. That sentence sounds bigger than an ice cube deserves. It is not. The ice cube in your glass is a small version of the same mechanism that kept Earth's oceans from freezing solid. Through every ice age this planet has experienced, the same accident of chemistry that made your cold drink work is the reason complex life exists at all on this planet. It is so familiar that almost nobody has ever stopped to ask why it happens, or what would be different if it did not. Most solids behave the same way when they freeze. The molecules slow down. They get closer together. The solid packs more tightly than the liquid it came from. That means the solid is denser. Denser means it sinks. This is normal. This is what physics expects. Water follows this rule down to 4 degrees Celsius. Cool liquid water toward that temperature and it gets denser, exactly as predicted. But below 4 degrees, something different begins to happen inside the water. Water molecules are not simple. Each one is 2 hydrogen atoms bonded to 1 oxygen atom, and the geometry of that bond is asymmetric. The molecule has a slight electrical imbalance. One side carries a weak negative charge, the other a weak positive charge. This asymmetry is why water molecules attract each other. The negative side of one molecule is drawn toward the positive side of a neighbor. These attractions are called hydrogen bonds. They are roughly 20 times weaker than the bonds holding each water molecule together internally. But there are an enormous number of them, and at low temperatures they start to dominate. Below 4 degrees, water molecules begin locking into a rigid, crystalline structure held together by those hydrogen bonds. The structure they form is specific. It is not random packing. The hydrogen bond angle forces the molecules to arrange themselves at particular fixed distances. Those fixed distances are wider than the distances between molecules in liquid water. The crystal lattice that forms when water freezes is a more open, more spacious structure than the liquid. Ice takes up more space than the water it came from. It is less dense. It floats. That geometry is the accident. The reason water is unusual at this level goes back to the bond itself. Most molecules with similar small sizes, ammonia, hydrogen sulfide, methane, do not form the same persistent network of attractions between neighbors. Their solid forms are denser than their liquids. Water's specific bond angle is roughly 104 degrees between the 2 hydrogen atoms. That geometry creates a polarity. One end of the molecule carries a weak positive charge, the other a weak negative charge. The attraction between neighboring molecules is unusually persistent, even as temperature drops. The network of attractions that water molecules form in liquid water is already distinctive. When freezing locks that network into a rigid geometry, the result reflects the specific angle at which the hydrogen atoms sit relative to the oxygen. That angle. Nothing else. Everything downstream, the open lattice, the floating ice, the insulated oceans, follows from electron count and geometry in a single atom. No engineer designed the hydrogen bond angle. No evolution selected for the density outcome. The water molecule has the shape it has. That shape happens to produce a crystal lattice less dense than the liquid it came from. Change that bond angle slightly and the lattice closes up. Ice sinks. The physics of what follows is not complicated, and it is not survivable. In winter, surface water cools. In a world where ice sinks, the moment that surface water reaches freezing, it freezes. Then it sinks. The bottom of the lake gains a layer of ice. The now ice-free surface is exposed to cold air again. More water cools, more ice forms, more ice sinks. The process repeats. There is no insulating cap on the surface. Nothing slows the heat loss. Nothing protects the liquid water below from the cold above. The lake freezes from the bottom up, layer by layer, until the entire body of water is solid. The sequence is not gradual. Once surface freezing produces sinking ice, the process does not slow as the water cools, it accelerates. Each sinking layer of ice removes thermal mass from the bottom of the lake and replaces it with a cold, solid barrier. The remaining liquid water above it has no stored heat below to draw on and no insulating cap above to protect it from the air. Heat loss is direct and continuous. In real winters, deep lakes stay liquid because the surface ice cuts the rate of heat exchange between water and air by roughly 90%. Without that cap, the rate of freezing is determined only by how cold the air is and how much exposed surface remains. In extreme winters, that means total freezing in weeks. In moderate winters, it means months instead of seasons, but the end state is the same. This is not the same as lakes freezing in the world you live in. In the world you live in, ice forms at the surface and stays there. That floating layer is less dense than the water below, so it cannot sink. It sits on top, and it acts as insulation. The ice layer has low thermal conductivity. Heat does not move through it easily. The cold air above the ice cannot efficiently reach the liquid water below. The lake loses heat slowly. Deep water stays liquid. At the bottom of a deep lake in winter, the temperature is roughly 4 degrees Celsius. That is the temperature at which water reaches its maximum density and settles to the floor. That pocket of slightly warmer water is not a coincidence. It is a direct consequence of ice floating. It is the refuge where aquatic life survives every winter on this planet. It exists only because the ice stayed on top. Remove the floating ice and you remove the refuge. The bottom of the lake is the first place to fill with ice, not the last. The 4-degree pocket disappears before it can form. Winter does not create a frozen lid over a living lake. It creates a solid block of ice where the lake used to be. In 1962, the paleoclimatologist W. Brian Harland at Cambridge University began assembling geological evidence from multiple continents. The evidence was from ancient rock formations, specific types of sediment and mineral deposits that only form under glacial conditions. The deposits were not from the poles. They were from the tropics, from rock layers that 700 million years ago would have been at sea level near the equator. Ice at the equator, glaciers covering the tropics. The evidence pointed toward an event that became known as Snowball Earth. Ice extended from both poles all the way to the equatorial regions. The planet came within a narrow margin of freezing over entirely. Harland's analysis took years to compile and was disputed for years more because what it described was so extreme it seemed implausible. But the geological record refused to change. The planet had nearly become a permanent ice ball. It escaped only through millions of years of volcanic activity pumping carbon dioxide into the atmosphere. That greenhouse gas buildup was slow enough that it would have taken 4 to 10 million years to melt the ice. Even after the spreading stopped, Earth survived Snowball Earth, barely. And that near miss happened with ice that floats. The Snowball Earth event Harland documented was not a brief cold snap. The geological record suggests the ice persisted for millions of years. Earth's escape from it was not active. No biological intervention, no planetary thermostat that kicked in. The planet simply continued to experience volcanic eruptions during the entire frozen period. Volcanoes emit carbon dioxide regardless of surface temperature. Carbon dioxide builds up in the atmosphere regardless of whether the surface is liquid or solid. Over millions of years, enough CO2 accumulated to trap enough solar heat to begin melting the equatorial ice. Once melting started at the equator, the feedback ran in reverse. Less ice, lower reflectivity, more heat absorbed, more melting. The recovery was abrupt relative to the glaciation, but it still took hundreds of thousands of years. Life survived Snowball Earth in isolated pockets of liquid water, hydrothermal vents, thin liquid layers under equatorial ice where geothermal heat reached the surface. The floating ice insulation protecting those pockets was the only thing that kept the biosphere from total collapse, one of the most extreme climate events in Earth's history. Survived because the ice floated. Run the same scenario in a world where ice sinks and the near miss does not stay a near miss. In a world where ice sinks, the glaciation of a lake is total. The glaciation of a sea is total. As ocean temperatures drop, surface water freezes, the ice sinks, and the water column freezes progressively from the bottom up. The insulating surface layer that protected the oceans during every real ice age does not form. Oceans that would have remained liquid under floating ice insulation instead freeze solid. And frozen oceans do something specific to Earth's climate that makes everything worse. Ice is white. White surfaces reflect sunlight rather than absorbing it. Open ocean is dark. Dark surfaces absorb sunlight. The fraction of sunlight a surface reflects is called its albedo, and it determines how much solar energy the planet actually absorbs. An ocean covered with permanent ice reflects far more sunlight than an open ocean. Less absorbed energy means a cooler planet. A cooler planet freezes more water. More frozen water reflects more sunlight. A cooler planet still, more ice. The cycle has no internal break. Once ocean ice coverage reaches a critical threshold, roughly 30 degrees of latitude from the poles, the feedback becomes self-reinforcing. The process runs to completion. The planet does not partially freeze. It freezes entirely. You would still be alive, a viewer at this point might think. Not in the oceans, but somewhere, near geothermal vents, deep underwater, in hot springs. Extremophiles survive in conditions far worse than a frozen ocean. If ice sank and the planet froze, life would persist in the cracks and the heat seams. Evolution would find a way. This is true for microbes. It is not true for you. Geothermal vent ecosystems are real. Microbial life thrives in water temperatures that would kill any mammal, in chemistry that most organisms cannot tolerate, in complete absence of sunlight. Those ecosystems exist today and would exist on a frozen-over Earth. But they are isolated. They are small. They are chemically extreme. A vent system cannot support the entire biosphere. Isolated, hot chemistry niches do not sustain complexity at the scale that surface ecosystems do. The geothermal vent answer fails in another specific way. Geothermal vent ecosystems require geological activity, tectonic movement, undersea volcanism, the circulation of heated water through oceanic crust. These processes are real, but they are localized and unstable over geological time. A vent system that exists today may not exist in 1,000 years. The diversity of complex life on Earth did not emerge from a single thermal niche. It emerged from an interconnected web of environments. Shallow coastal seas, freshwater lakes, rivers, wetlands, tropical reefs, open ocean. That web requires liquid water everywhere simultaneously, not just in volcanic seams at the ocean floor. Geothermal vents are fascinating precisely because they demonstrate that life can persist at extremes. But they are a backup system. They were never the engine. Hundreds of millions of years of evolution produced fish, amphibians, reptiles, and mammals. All of it required persistent liquid water environments at the surface. No frozen ocean provides that. Every multicellular organism, every ecosystem built on photosynthesis, every food web that starts with sunlight hitting liquid water, all of it collapses. Complex life did not emerge from extreme niches. It emerged from the open water that those niches could never provide. And the open water existed because the ice stayed on top. The same molecular geometry that put the insulating cap on every ocean and lake on Earth has another effect you have already experienced. Water expands when it freezes. The crystal lattice takes up 9% more space than the liquid water it replaced. If water is inside a closed container when it freezes, the expansion has nowhere to go. The container cracks. Pipes burst in winter because the water inside them expands into the pipe walls with enough force to split metal. Rocks crack in mountains because water seeps into fissures, freezes, and forces the fissure open. Pavement heaves and potholes form for the same reason. The property that cracked every pipe in human history is inseparable from the property that kept the oceans from freezing solid. Same geometry. 20 ice ages survived. There is no version of water that floats as ice without also expanding as ice. The open crystal lattice creates both properties simultaneously. You cannot have one without the other. Ice is approximately 9% less dense than liquid water. That is the specific number, not 1%, not 50%, 9%. Ice sits mostly submerged. About 90% of an iceberg is below the waterline. The 10% visible above the surface is the exposed portion of a density difference that holds up the entire thermal management system of the planet. A slightly different bond angle, a slightly tighter crystal lattice, a density difference of 0 instead of 9%. The ice sinks, the insulating cap never forms, the glaciation runs to completion. The evolutionary pathway that produced complex life never opens. The water molecule has the shape it has. The lattice forms the way it forms. The ice floats. Everything else, the lakes with liquid bottoms, the insulated oceans, the survived ice ages, the biosphere, is a consequence of one geometric accident. Repeating in every water molecule on the planet simultaneously, the next generation of exoplanet telescopes will look for signs of liquid water on distant worlds. Some instruments currently in development are designed to study the atmospheric chemistry of planets in other solar systems. They will measure reflectivity and temperature. They will look for biosignatures, chemical markers that suggest life is altering a planet's atmosphere. They will not be able to determine whether the solvent on those planets has the same anomalous density relationship that water has on Earth. A planet with water at the right distance from its star could still be a frozen ball if its ice sinks. The presence of water is not sufficient. The geometry of the water molecule is also required. And no telescope we will build in the foreseeable future can read a bond angle from light years away. Earth had the distance right and the molecule right, both at once. The odds of that combination are not something any instrument currently measures.